What is going on, everybody? Welcome back to my YouTube channel, Richard on Data. And if this is your first time here, my name is Richard, and this is the channel where I help you break into data science and grow your skills in the field. This is another video in my R tutorial series, and specifically, it's the third and final video in my series covering the Tidymodels suite of packages for machine learning. So if you haven't seen the first two videos, they will be in the description of this video. Highly, obviously recommend watching those two before getting into this one. But where we left off in the last video was we had just gone through workflows. So a workflow is just a container which puts all the pieces of the machine learning pipeline into one condensed object. So we had done in the last tutorial a random forest where we'd specified to the mtry hyperparameter that we're going to tune that later. That's why we passed this tune function to the mtry hyperparameter argument here. But then even things like the recipe, which contains things like the pre-processing steps and downsampling of the training set, that goes into the workflow as well as this model. And then that workflow, we're going to fit that to our training set. We did that. Then we evaluated the performance on the testing set. We found that there was overall a hit to accuracy here when we introduced downsampling, but our sensitivity and specificity are a little bit more balanced. Like I just pointed out though, we specified for this mtry hyperparameter that we're going to tune it later using this tune function here. And that's where this tune package in Tidymodels is going to come in. That's the first thing that we're going to cover in this tutorial. So if all that sounds good to you, smash the like button to this video and keep watching until the end. Also subscribe to my channel if you haven't already and hit the notification bell so YouTube notifies you whenever I upload a video. Then lastly, if you guys would be willing to support me above and beyond that, I do have links in the description of this video to things like my Patreon account, PayPal account, and my crypto wallet addresses. Your support is highly appreciated. And then of course this script will be available on my GitHub repo. You can also find that in the description of the video. Now, without further ado, let's get started. So if you've seen my Caret tutorial series, or if you're just generally familiar with the Caret package, then you know all about the train control function out of Caret. So what I would commonly do in the tutorial series was I would want to do a 5-fold repeated cross-validation resampling approach, but then I would also define what's known as a tuning grid. So a tuning grid is nothing more than a manually specified range of values that I would want to search for my hyperparameter, with the goal of optimizing some metric like area under the receiver operating characteristic curve. Well, we're going to do those exact same steps using the Tidymodels framework here. Now, when we do 5-fold cross-validation, that means that we're essentially splitting our data into 5 roughly equally sized groups. Now, those equally sized groups are known as the folds. So when you hear me refer to folds, well, that's what we're talking about. Now, that entire process is repeated multiple times. That's where the repeats equals 5 comes from. But the first thing that we're going to do is we're going to store those folds in their own object. Now, to do this, we're going to use this vfoldcv function, which comes from the R sample package. That's actually the very first package in Tidymodels that we worked with at the beginning of this tutorial series, but the configuration for however you want to do your resampling is going to come in here. So v equals 5, repeats equals 5. We're going to store that in this folds object. Okay, moving on to the next step, we're going to specify the tuning grid. We're going to do this by using the expand.grid function, and we're going to specify we want to search over a range of mtry could be 3 to 15. Now we're ready to rock and roll. From that workflow that we created earlier, we're going to pipe to it the tune grid function. To the resamples argument, we're going to pass the folds that we just defined. To the grid argument, we're going to pass this RF grid object we just defined. That just contains the values of mtry we're going to search over. Then we're going to specify the metrics that we're interested in. Now, I'm going to specify the area under the precision recall curve and the area under the ROC curve. Now we're going to pipe to that this collect metrics function, and then bam, we have a whole lot of different results here for the various values of mtry that we were searching over. Now, this is a lot of super helpful information. I see a lot of times area under the precision recall curve is less than 0.5. Area under the ROC curve seems to be hovering around 0.63 or 0.64 a lot of the time. This is too much output to sift through, and we want a robust way of actually looking through this. So I'm going to come up with a programmatic way of finding what our optimal value of mtry could be. So I reported area under the precision recall curve here before, but maybe I'm more interested in the area under the ROC. So let's filter down to a metric of ROC underscore AUC. Now we're going to find the row which maximizes the mean ROC, or area under the ROC in this instance. So let's programmatically pull what value of mtry that is out. Then we're going to pass that to the mtry argument to random forest. So do you see what I did there? Store to this mtry object here the best performing mtry, and then just go through the training process like we did before. Okay, fit that to the training set. Then let's go ahead and generate our predictions in a probability form. Now notice here when I generate predictions for the test set classes, take a look at this observation here for instance. It gives us two columns. One is the probability of being in the bad class. One of them is the probability of being in the good class. Take this first observation here. The probability of being in the bad class is 0.054. The probability of being in the good class is 0.946. Now, if we return these probabilities in just the class prediction form, what it would do is, say the probability of being in the bad class is 0.5 or higher, like these observations are. Well, those are the observations which are going to get predicted to be in the bad class. That threshold for being classified in the bad class is 0.5. Well, you can go in and just manually create your own predicted class values by playing with this output. Say, for instance, you just want to generate your own vector of class predictions by taking the bad class, and then when it's the bad class probabilities here, and then whenever it's, let's say, 0.333 or higher, let's just assign those observations to the predicted bad class. So you can go ahead and do that, kind of manually altering that threshold for what you're predicting to be in a given class. And in fact, that's one of my preferred methods of correcting for class imbalance. You saw in the previous tutorial, we tried downsampling as an approach for dealing with class imbalance. So we're not going to walk through a full example of this kind of approach here, but just know that that's an option that you have at your disposal that is oftentimes quite powerful. So the next thing that we're going to do here is create a visualization of an ROC curve. And if you've gone through my Caret tutorial series, the steps here are completely identical to the steps there. So what we need here are two objects. One containing the predictions and one containing the labels. By the way, all this is coming from the ROCR package. Unfortunately, that's neither in the Caret framework or the Tidymodels framework, but it's the best visualization package for ROC curves at this time that I'm personally aware of. So for the predictions object, the syntax here is a little bit strange because it's not super clear. Well, do we want the probabilities for being in the good class or the bad class? So it's not super clear, but so you'll have to trial and error it a little bit. But typically I've found if you pass the probability predictions for the majority class to it, that's the one that it wants. So again, just trial and error this if you run into problems. Then obviously for the labels, that's the source of truth. That's the class variable from the test set in our case here. So these two objects are going to get passed to the prediction function. Again, this comes from the ROCR package. So we're going to create this object here called pred. Okay, well, that's going to get passed to this next function performance, which that creates an object based on the metrics that we want to actually visualize. So think about what an ROC curve actually is. An ROC curve is going to visualize the true positive rate, that is sensitivity, against the false positive rate, that is 1 minus specificity. So if you go into the help documentation for the performance function, you can find all the different metrics that you can visualize. But I'm going to pass as arguments to the performance function TPR for true positive rate and FPR for false positive rate. So we're going to create a plot of that. We're going to just specify to this argument average equals threshold and then colorize equals true. Now, you're probably going to know that your ROC curve looks appropriate if the body of the curve is over the diagonal line going from 0, 0 to 1, 1. If it's above that diagonal imaginary line here, that tells you the area under that curve is greater than 0.5, meaning for this part right here, that means you probably got it right. So we've created our visualization here. This is a beautiful thing to include in reports or applications which describe how well your classifier is actually performing on the testing set. So a great thing to have in your toolbox here. Now we've saved the best and most exciting topic in this Tidymodels tutorial series for last, and that's going to be stacking or ensembling the predictions from various models. So let me put it this way. I want to take a random forest classifier, a k-nearest neighbors classifier, and a support vector machines classifier, and put all of those together into one, for lack of a better term, super classifier. Well, Tidymodels is going to make that super easy for us. Okay, so let's start with the random forest model, and I don't even need this line of code here, but I'm just including it here so you remember we defined a random forest model earlier, but we need to define the specifications for the k-nearest neighbors and for the support vector machines. So what I'm going to do here is we use this nearest neighbor. Like, remember, you can go up here and search for your parsnip model specifications through a UI if you prefer to do it that way. But basically, we need mode equals classification. And then for the neighbors argument, that's a hyperparameter to k-nearest neighbors. I'm going to specify I want to tune that later. The engine for this is going to come from the KKNN package, which I loaded at the beginning of this script. And we're going to go through a similar process for the SVM model. Specify the SVM underscore RBF function, which under the cover specifies that we want a radial kernel for support vector machines. This is going to have two hyperparameters, cost and RBF sigma, which, again, we're going to tune both of those later. The engine is going to be the kernlab library, which, again, we loaded at the beginning. Now, for each of these models, we need to create a workflow. The random forest workflow has already been defined, so the workflow for k-nearest neighbors and support vector machines, it's totally straightforward. We're going to specify the down recipe, which we created before for the random forest. The same thing is going to work for k-nearest neighbors and support vector machines. Just pipe after the recipe, the models that we defined, and we are ready to go. So all this code is going to look remarkably similar to what we just ran before. The only difference is for later, we are going to need this control stack grid thing here. So that's just another argument that's going to go to the tune grid function. But now here, instead of manually specifying the range of values that we want to search for over the hyperparameters, we're just going to specify, just be smart about it and just specify the number of different values of hyperparameters we want to search over. So if you know the tune length of argument from Caret, it's just analogous to that. We're just specifying, just try 7 different values for hyperparameters for each of these classifiers. So I'm also not even going to look over the area under the precision recall curve. All I want to do is find the value of these hyperparameters that maximize area under the receiver operating characteristic curve. Okay, go from there. The syntax looks just like it did before. All of this so far has largely just been a setup to the real meat and potatoes of the stacks package, and that's what we're going to get into here. So stacks, much like Themis, as we saw earlier for the downsampling and the upsampling, this is another package outside of the core Tidymodels ecosystem that you are going to have to load separately from Tidymodels. But let's get into the real beauty from this package. So to start stacking the predictions from various classifiers, we have to start by defining a data stack object. So this type of code is analogous to like initializing a ggplot object using the ggplot function. We're going to start by initializing this with the stacks function and then pipe to it various candidates. So the candidates are all these definitions for classifiers that we defined up above. So all these resamples that we defined for the random forest, the k-nearest neighbors, and the support vector machines where you have various different configurations for hyperparameters. All of those are candidates, and they're going to get piped to this data stack object up top here. Makes sense? And you can just call the credit stack object, which I just defined up here, and it'll just give you some basic information. It's just a data stack with 3 model definitions and 21 candidate members. 7 model configurations for random forest, for k-nearest neighbors, for support vector machines, etc., etc. The next step is we're actually going to blend the predictions from these various candidates. We're going to do this using an aptly named blend predictions function. Now, how this works is it evaluates your data stack by fitting a regularized model on the assessment predictions from each candidate member. And to do this, it uses a lasso model. So lasso being a common regularization technique, it's going to assign each of these candidates a beta parameter or a weight. And now, if the weight is greater than 0, then that candidate gets kept. If the weight is equal to 0, then that candidate gets dropped. So the argument that you do need to specify here is the penalty factor. And if we look at the documentation here, it can range all the way from 10 to the negative 6, all the way up to 10 to the negative 1. So I'm just going to kind of arbitrarily select a penalty equal to 0.001. And then we create this new credit model stack object, and I find that the weights on here's a random forest candidate, here's another random forest candidate, and here's a support vector machines candidate. It turns out those were the only 3 candidates which returned a weight greater than 0. There's more information if you look at this part of the output from the R console, but the real meat and potatoes of the output here is this tibble that gets returned. And then similarly, if you want to use the autoplot function, you can go ahead and create a visualization of these stacking coefficients. There is one final step that we need to do here in order to fit the model stack members with non-zero stacking coefficients. And so all we have to do to the stack that we've created in this pipeline we've been working through thus far, all we need to do is pipe to that the fit members function. So just do that, and now we are ready to use this supermodel as I've been defining it. Basically, a model that combines the predictions from these various different candidate models that we've been working with. We are ready to evaluate the performance of that thing on the testing set the way we have any other classifier we've been working with in this tutorial series. So the syntax for that looks exactly the same as everything we've been working with so far. When we evaluate this thing on the testing set, we see the accuracy is actually worse than the very first model that we fit at the beginning of this tutorial. And we're back at the same problem where we have fairly imbalanced sensitivity and specificity. So this, I think, really speaks to a broader, just philosophical concept that the more complicated model is not always a better one. Now, I've been generally working with a fairly simple approach here, and maybe I could go ahead and make this thing even more complicated by just adding more and more candidates, specifying maybe a greater length of possible values of hyperparameters that I wanted to tune over. But at the end of the day, sometimes, regardless of what your intended outcome is, a simpler and more parsimonious model may be better. So I'm going to leave you there. Hopefully you've enjoyed this series on Tidymodels. Hopefully you've gotten something out of it and you know how to use these packages to tackle the next machine learning problem that you work on. So if you enjoyed this video, please consider sharing it, smash the like button. Also leave me a comment down below and let me know, do you like Caret more? Do you like Tidymodels more? Which one's easier? Just start a discussion down in the comments down below. Then I'll see you all in the not so distant future. Until then, Richard on Data.